Hello, welcome back. Today we're going to have an application of integration. It's in fact finding the area between a curve and the x-axis and two vertical lines. But to achieve our goal to sort of like calculate the definite integral, we're going to sort of like adopt a change of variable idea to convert the given integral to something simpler than that. All right, let's read the question. So the question is asking to find the area of the region bounded by the graphs of the equation. So the first one is this x times the exponential function. And x equals 0 is the y-axis, y equals 0 is the x-axis, and you have the vertical line x equals radical 5. And we can use a graphing utility to graph the region and verify the results. So if we graph x times e to the minus x squared plus 4, and the vertical line x equals radical 5 together with x and y axes, we get this kind of region. And the area between the curve and the x-axis for those x values can be written in terms of an integral. In fact, that integral is going to be something from 0 to radical 5 of the function e to the minus x squared over 4 dx. So whatever the value of this integral is would be the orange area. Okay, so I'm going to call this A. So that represents the area of the orange region. As you first look at this, it doesn't look like you can do the integration in one shot unless you have a change of variable. All right, this is a definite integral. We don't need to worry about the limits at this moment. If you want, we can just remove the limits just to find the antiderivative of this function on a side piece of paper. So you can actually work through the problem the same way on your scratch paper. So here that if you did not have x and if you had only x here, so you would talk about the integral of e to the x, but we have, or minus x, that would be easy to integrate. But here, the fact is that the exponent has something to do with this x here. In fact, if you call the exponent all the way to be a new variable u, and if you take the differential of u, you will have u prime dx, but u prime is negative 2x dx. So that's good news because I can sort of like replace x dx by the corresponding du version of that. And I have already called the exponent to be u, so that the u integral is going to look like this. So the u integral, well, x dx, right? X dx is negative 1/2 du. So we can pull out negative 1/2 and write du here. And obviously this term here, the exponential term, is going to be just e to the u. So this integral here has a very nice newer version because we know how to integrate e to the u du, for which you can use the differentiation formula card to get that this is equal to negative 1/2 e to the u plus c, but we don't really put the plus c here. But let's go back to the original variable here. Negative 1/2 e to the minus x squared over 4. Okay, so remember that for definite integrals, we only need an antiderivative of this function here, x e to the negative x squared 4, and we found that antiderivative, so we don't need to put an integration constant here because eventually we're going to do definite integration. Okay. So then I go back here, since I know the antiderivative of this function, that's negative 1/2 e to the minus x squared over 4, I use the notation, the bracket notation here. I put the lower limit here and upper limit here. And then the value of the integral is going to be the top limit plugged in, so negative 1/2 e to the negative radical 5 squared, that's 5 over 4, minus negative 1/2. When you plug in 0 for x, so the exponent is going to be 0, e to the 0 is going to be 1, it's just going to be negative 1/2. And to simplify, As you see, this is equal to 1/2 minus 1/2 e to the -5/4. Okay, so this is the value of the definite integral, but that corresponds to the area between the curve x times e to the -x² plus 4 and the x-axis. Another way to handle this problem is that to convert the whole definite integral to another definite integral with the newer variable. So we could perfectly do that as well. In fact, let me clean this and I'll show you how this works. All right, the other technique, we can start from here. In fact, after we found the right of change of variable, in fact, we wrote this as -1/2 e to the u du, but the original integral was a definite integral. Why don't we have a definite integral, but the limits are written in terms of u? So here is how that works. So as you see that the lower limit here is x equals 0. And then we have this change of variable here. This is the equation that we're going to use. Why don't we plug in 0 for x here? So when you do that, this whole right-hand side is going to be 0. Then u is going to be 0. So that's going to be our lower limit. Okay? And for the upper limit, x equals radical 5. When you plug in here, that's radical 5 quantity squared. And that's 5. So if you simplify this expression, it's going to be -5/4. So at this stage, we have an integral written in terms of u, but the limits as well are written in terms of u. All we're going to do is to evaluate this integral, and the value of this integral is going to be the same as the value of this integral. So you remember that we integrated this as like e to the u. So now I'm going to use the bracket notation, 0 and -5/4. I'm going to write the result right here because two integrals are the same. They have the same value. So now with the bracket notation, I'm going to use the upper limit to plug in. So it's going to be -5/4 minus, I'm going to use the lower limit plugged in. So e to the 0. Okay. So minus minus becomes plus, and e to the 0 is 1. So in turn, you have 1/2, which is this guy, minus 1/2 e to the -5/4, which is exactly the same value that we found a few seconds ago. Okay? But this way, we also converted the definite integral all the way into something written in the new variable so that we just did not need to go back to the original variable to find the value of the integration. So speaking of the area that was being asked in the beginning of the question, the value of the area is exactly this number. You can go ahead and use your TA84 to get an approximate value of that, but I just want to end this here with the exact value of the area. All right, this ends the video. Thanks for watching. I'll see you in another video. Bye.